This is the 47th video on Newton's laws of motion. This is in continuation of the 46th video. In this also I'll take up a numerical problem based on blocks, wedge and pulleys and strings, similar to the problem discussed in the 46th video. Okay. First what I'll do, I'll draw the diagram of the situation. So the diagram is this. This is a smooth horizontal surface. Okay. Here there is a wedge, a rigid wedge of mass 4m. This is a smooth inclined surface of the wedge. The wedge incline makes an angle of 30 degrees with the horizontal. Here there is a pulley P1, which is rigidly fixed to this wedge. And here there is a block of mass m attached to this pulley by means of a string. Okay. This string continues ahead and is in contact with another pulley. And again it comes in contact with another pulley. Again it comes in contact with that like this, see, like this. So this is the situation. Alright, fine. So this is a smooth horizontal surface. This is a rigid wedge of mass 4m. This is a smooth inclined surface of the wedge. This is a block of mass m. This is connected by means of a string to these pulleys and wall and wedge as shown here. All the pulleys are massless. So we take this pulley as P1, this pulley as P2, this pulley as P3, and this pulley as P4. All the strings are massless and inextensible, and there is no friction anywhere. All these 4 segments of string are horizontal. This pulley is also massless. Okay. This is the situation. There is no friction anywhere, as I repeatedly told you. Question is to find the acceleration of wedge with respect to ground. Find the acceleration of wedge with respect to ground. Find the acceleration of wedge with respect to ground. Okay. After the system is released from rest. Is released from rest. Okay. ये हमें पता करना है. This we have to find out. This one I rub it. Okay. So first what we'll do, we'll show all the accelerations. Okay. So when the system is released from rest, this block wedge of mass 4m, wedge will be denoted by W, and this block will be denoted by P. So with respect to ground, this 4m will accelerate rightward with some acceleration a with respect to ground. Okay. So AWG, acceleration of wedge with respect to ground, W for wedge, is a in rightward direction. Okay. And with respect to wedge, the block of mass m will move with some acceleration b with respect to wedge. So b is the acceleration of block ACCM, meaning acceleration of block P with respect to wedge. Okay. This is the acceleration of block P with respect to wedge B. Alright, fine. Now one more thing. I'll show the tension in the string. The string is massless and there is no friction between string and pulley anywhere. So tension at all points of the same string is T. Say T. Okay. Fine. Alright. So first what I'll do, I will write down the Newton's law equation of block with respect to wedge down the incline. For that what I'll do first, I'll draw the free body of this block with respect to wedge. Okay. So I'll draw the free body of this block of mass m. Real forces will act on it as shown. mg, T and N. These are the 3 real forces on the block P. Now this wedge accelerates with respect to ground. So this wedge is a translating NIRF. So as seen from wedge, a pseudo force will act on the block in leftward direction opposite to that of vector A. Its magnitude will be ma. Okay, fine. Now I write down the Newton's law equation of block with respect to wedge down the incline. So down the incline, which forces are going to act? Mg sin 30 degree, that is mg by 2, plus ma cos 30 degree minus T is equal to mb. This is therefore the first equation. Okay. Now what I'll do, I'll write down the combined equation of motion of wedge plus block in rightward direction. Okay, but before doing that, I would like to explain one thing. One thing I would like to explain. See, take this pulley P1. So this one I rub, okay. Take this pulley P1. This is a pulley P1, okay. This is a string which passes over P1. You can see that the string covers half portion of the pulley. If the radius of pulley is r, then circumference of this pulley is 2 pi r. Then string is in contact with pi r length of the pulley on its circumference. So at every point on this pulley P1, the string exerts a normal contact force. There is no friction, okay. Now if you find the resultant of these normal forces, then in vertical direction these normal contact forces will have zero resultant. And resultant of these normal forces will be only in the leftward direction, okay. Let this be the highest point of pulley, say P dash, and let this be the lowest point of pulley P1, P double dash. So in this, these arrows which I have shown, what are they? They are the normal contact forces on pulley P1, where the string and P1 are in contact. If you find the resultant of these normal contact forces, they will cancel out in vertical direction. Only leftward direction will remain. So effectively we will say that this string exerts a force of T at the highest point P dash of pulley P1, and this string exerts a force of T at lowest material point P double dash of pulley P1. So we will say that effectively if you find the resultant of these forces, this will be T in this way and T in this way. One thing I'd like to make it clear, we'll say that effectively now string exerts force on this pulley P1 at only two of its points, at points P dash and points P double dash. Okay, so we'll say that this string exerts force on pulley P1 effectively at only 2 points. First, at its topmost point P dash, string exerts a force T in this direction, and at its lower material point P double dash of pulley P1, where it exerts T leftward direction. Same argument applies to P2, P3 also. Okay, same argument, same. Okay, and now take this pulley P4. See, if I take this pulley P4 I take it, then what do we see? Like this. This is pulley P4. Now this is the center of the pulley P4. See, the string is in contact with this much portion of the pulley. Okay, this string is in contact only with this much portion of the pulley. This is the highest point of pulley. Let's call it, say, B dash. And this is the point of the pulley where the string just loses contact with the pulley. Let's call it as B double dash. So now string is in contact with this much portion of the pulley. Now at every point of this, string exerts a normal contact force on the pulley. If we find the resultant of these normal forces by resolution, then we'll say that this string exerts only a force T at highest point B dash of the pulley, and this string exerts a force at other point B double dash only, T in this direction, and this is B dash. So in this here we'll say effectively that this string exerts a force at only 2 points of pulley P4, at point B dash and point B double dash. At point B dash, string exerts a force T rightward, and at point B double dash exerts a force T down the incline. Okay, so this will say effectively, this will say in equivalent, these two are equivalent situations. Alright, fine. Now, what I'll do, I'll write down the combined equation of motion of wedge plus block in ground, wedge plus block. Now, in the combined equation of motion theory 19th video of Newton's laws, everything has been told. So in combined equation, only external forces will appear. So and it is always written with respect to ground, so only real forces, no pseudo forces. So for that, first what I do, I draw the free body of block and wedge with respect to ground. Okay. So see, what are the forces? mg, real forces, T and N, that's all. This is the free body of block with respect to ground. Okay. Now I draw the free body of wedge with respect to ground. Okay. So what are the real forces on the wedge? 4 mg, N1 on the wedge due to ground, N on the wedge due to block as per Newton's third law. Now this string exerts a force on P4 at 2 points B dash and B double dash as shown here. So this P4 I am taking to be part of the wedge itself. So here I will say T in like this, and here T in like this. This T I have shown here. Now this pulley P2 is also a part of this wedge. So I draw the P2 here also. Now as I explained for pulley P1, same argument applies to pulley P2. So this string will apply force on P2 at only two of its highest points effectively. It will be like this, T in this way, T in this way. Okay, and this string is attached to wedge at this point. So it will exert a force T in rightward direction. Okay, so I think this is the free body of the wedge with respect to ground as I have shown it here. Alright, fine. Now, I'll rub this one, okay. Now, write down the combined equation of wedge plus block with respect to ground in rightward direction. So, now in combined equation only external forces appear, no internal forces. In this diagram, N and N are internal forces, they will not appear in combined equation. This T and T, they are also internal forces, they will not appear in combined equation. So only external forces in the system are mg, 4mg, n1, t, t and t. Now we are writing down the combined equation rightward direction. So only these forces, external forces, will have no component, right angle. Only component of these forces, 4t, will be there. So total external force on the wedge plus block system in rightward direction is 4t. So 4t is equal to 4m into acceleration of wedge with respect to ground, which is simply a, plus mass times. Now here what term we have to write down? The component of acceleration of block with respect to ground in rightward direction. Okay. Suppose I take the rightward direction to be x-axis. So here I write down the name of the basic acceleration term. So that will be x component of acceleration of block with respect to ground. X component of acceleration of block with respect to ground. Okay. So this I write in this way. 4ma plus m times. Now this I express as a dot product. APG dot I hat, where I hat is a unit vector along x-axis. Alright, fine. So this is 4t is equal to 4ma plus m times. Now from the theory of translating frames, APG will be written as APW plus AWG dot I hat. Alright, fine. Now I rub this one, okay. Now I write down, what do you say here? I get 4t is equal to 4ma plus m times. APW is nothing but vector b, acceleration of block with respect to wedge, that is vector b. And AWG is nothing but vector a dot I hat. So we get 4t is equal to 4ma plus m. This will be b dot I hat plus a dot I hat. This will be 4t is equal to 4ma plus m times b dot I hat. Now what is b dot I hat? B is in this direction, I hat is in rightward direction. So dot product becomes b into 1 into cos of angle between b and I hat, which will be 150 degree. Cos 150 degree becomes minus root 3 by 2 plus a dot I hat. That becomes a into 1 into cos 0 degree, which is simply a. So this is the combined equation of wedge plus block in rightward direction. Okay. So this one is a bit, okay, fine. So this is simplify, what do we get? We get 4t is equal to 4ma plus m times a minus b root 3 by 2. So I simplify it, I get 4t equal to 5ma minus mb root 3 by 2. This is the combined equation of motion for the wedge plus block in rightward direction. And this equation I'll write it here again for the sake of reference. I'll rub that just to get more space. So what do we get? mg by 2 plus ma root 3 by 2 minus t is equal to mb. This is the first equation. Fine. Alright. Now I rub this one, okay? This also rub it now. Equation has been written here, okay? Now, what I have to do next? I have to write down the constraint equation. That's the relationship between A and B. Now, constraint equation is a consequence of the fact that length of string is constant. Length of string is constant in every frame. So, we can write down the constraint equation any frame of reference. To illustrate the essential concept, I'll solve this equation in two different frames. First, I'll write down the constraint equation in ground frame. Then I write down the constraint equation in wedge frame. Both the methods I'll demonstrate. Writing down the constraint equation in wedge frame will be much more easier, but I'll demonstrate both the concepts involved. Okay. So now, first we write down the constraint equation in ground frame. Constraint equation in ground frame. So what is the basic idea? Total work done by string on all bodies in contact with it adds up to 0. Total work done by string on all bodies in contact with it adds up to 0. Okay. And work done will be written as force dot displacement. Since we are writing down the constraint equation in ground frame, so all the displacements have to be taken with respect to ground frame. Now see, this string, this is the only string in the problem. This string, like this one, like this. Now this string is in contact with wedge at this point. It is in contact with pulley at effectively, pulley P1 at effectively 2 points, topmost point P dash and bottommost point P double dash. Then it is in contact with pulley P2 at effectively this point and this point, as I have explained just now. This string is in contact with pulley P3 at effectively this point and this point. This string is in contact with pulley P4 at effectively this point and this point, as has been shown here itself. And then finally the string is in contact with block P at this point. So we have to write down the work done by string on all these bodies in time interval small t to t plus dt and equate the total sum of work done to 0. Okay. So we start from here. So this point, t acts rightward direction, and with respect to ground this is moving in dx rightward. As I said just now, we have to write down the constraint equation in ground frame. I am writing down. So t in this way, dx also with respect to ground. So t dx cos 0 degree, that becomes t dx. Now come to pulley P1. If you draw the pulley P1 here, then string effectively acts a force T at highest point P dash of pulley P1 and a force T at lowest point P double dash of pulley P1. Okay. Now these 2 points of pulley are at rest with respect to ground. So work done will be T into 0, that is 0. This also will do 0 work, T into 0, so 0. Alright. Now take the pulley P2. Now pulley P2 is in contact, rigidly attached to the wedge. It's a part of the wedge. So again, this string exerts a force at effectively 2 points on pulley P2. At topmost point T this way and at bottommost point T this way. Now this point we have to write down the displacement of this pulley P2 with respect to ground. Okay. So T acts in that direction, and displacement of this point with respect to ground is also dx, same as that of this. Okay. So this becomes T dx. Here also it becomes T dx. But before going, one thing I would like to explain. What is this dx? Dx is the displacement of wedge with respect to ground in time t to t plus dt. Okay. And dl is the displacement of block with respect to wedge in time t to t plus dt. This I would like to clarify. So dx, I write it here. It is the displacement of wedge with respect to ground in time t to t plus what? dt. And what is dl? dl is the displacement of block P with respect to wedge in time t to t plus dt. Okay. So t dx, so this point it becomes t dx, this becomes 0, 0, 2 zeros. This here t dx, t dx, t dx, t dx. Now take these 2 points. Now this string exerts a force T effectively at 2 points of P3, at its topmost point and bottommost point. So these 2 points are at rest with respect to ground. So this will be 0. So work done will be 0 plus 0. Now we come into this point P4. Now as shown on P4, string effectively acts at 2 points of P4, at this point and this point. Okay. So now this point P4 is rigidly fixed to the wedge. So P4 undergoes the displacement same as that of wedge, dx, in rightward direction. And T also acts in that direction. So work done will be T dx cos 0 degree. Simply T dx. Alright. Now take this point, B double dash. At this point T acts in this direction. And this point gets displaced dx in rightward direction. Angle becomes 150 degree, 30 interior angles, 150 degree. So work done becomes T dx cos 150 degree. So that becomes T dx cos 150 degree becomes what? Minus root 3 by 2. T dx minus root 3 by 2 it becomes. Alright, fine. Now come to this block. Now we have to write down the work done by this force T on block in T to T plus dt with respect to ground. But this displacement of dl is with respect to wedge. Okay. So now we'll write down the basic term, work done term. T dot displacement of block with respect to ground. So let's call it say ds. ds. So what is ds? ds is the displacement of block with respect to ground. Okay, in time t to t plus dt. Okay, fine. Now I love this one. Okay. So this I write here t dx, t dx, t dx, t dx. This becomes how much? 40 dx. 40 dx. This becomes minus t dx root 3 by 2. Now what about this t dot ds? This becomes t dot here, factor notation, dot ds. What is ds? ds is the displacement of block with respect to ground. So that will be written as displacement of block with respect to wedge, which is simply dl, plus displacement of wedge with respect to ground, which is simply dx. This all adds up to how much? 0. See, wedge is translating with respect to ground, okay? Wedge is translating with respect to ground. So constraint relative velocity formula for displacement and velocity are similar. Vpg equal to Vpw plus Vwg. Same way, displacement of block with respect to ground ds is equal to displacement of block with respect to wedge dl plus displacement of wedge with respect to ground dx. Same format, okay? Now this I expand it. 40 dx minus t dx root 3 by 2. So this I break. T dot dl plus t dot dx adds up to 0. Alright. So this becomes what? 40 dx minus t dx root 3 by 2. What about t dl? T is in this direction, dl opposite direction. So this becomes t into dl into cos 180 degree, which is minus 1. Plus t dot dx. T is in this way, dx is in this direction. Angle becomes 30 degree. So that becomes t dx cos 30 degree. Cos 30 degree becomes root 3 by 2. That adds up to 0. Now this term and this term go away. Now what do we get? 40 dx minus t dl is 0. Now t cancels out. 4 dx is equal to dl. So this is a relationship between displacements. But we have to find the relationship between accelerations. Now on this problem there are no variable angles. So displacement relation for constraint relation for acceleration is same as that of displacement. So corresponding constraint relation for acceleration will be replace dx by a, 4a, and replace dl by b. This is a constraint equation C. See, it was quite lengthy, you can see. We have got the constraint relation, but it was quite lengthy. This much we have to write down. Now, I've stated previously, we can write down the constraint equation in any frame, not necessarily in ground frame. Because length of string is constant in all frames. So I'll write down the constraint equation in the frame of wedge. Again, we'll get the same result, but we'll not have to carry out this much calculation. Alright, fine. So this are a bit, okay? So our constraint equation I write down in wedge frame. Now when I write down the constraint equation in wedge frame, then also the basic idea still remains the same. Total work done by string on all bodies in contact with it adds up to 0. And all work done have to be taken in wedge frame. So all displacements also have to be taken in wedge frame. Now again, this string is in contact with the wedge at this point. It is in contact with pulley P1 at effectively 2 points, this point and this point. It is in contact with pulley P2 at effectively 2 points, this point and this point. This string is in contact with pulley P3 at effectively 2 points, this point and this point. This string is in exerting force on P4 at effectively 2 points, this point and this point. And this string is exerting force on this block at this point. So all this work done have to be taken and added up and then equated to 0. But now all displacements we have to take in the frame of wedge. So I start from here. At this point, this is the material point of the wedge. T is acting in rightward direction. String exerts a force T. And with respect to wedge, this is at rest. So this string does 0 work on the wedge at this point. So 0. T into 0 becomes 0. Now take this pulley P1. If you take this pulley P1, effectively string acts at 2 points of P1. At its highest point P dash and lowest point P double dash. String exerts tension TT in leftward direction. Alright, fine. Now we have to take the displacement of these 2 points as seen from wedge, because we are acting on the constraint equation in wedge frame. Alright. Now see, displacement of wedge with respect to ground is dx rightward. Displacement of pulley P1 with respect to ground is 0. So in ground frame, wedge is undergoing a displacement dx in rightward direction, dx. and pulley P1 is fixed in ground frame. So as seen from wedge frame, pulley P1 will appear to move in leftward with a displacement of dx. So this point of P double dash will move leftward distance dx as seen from wedge. This point will also move leftward a distance dx with respect to wedge. So this T will do how much work on P double dash? T dx cos 0 degree. So it becomes T dx cos 0 degree. And this T also becomes at this point P dash. This also moves dx leftward with respect to wedge. So this also work done becomes T dx cos 0 degree into T dx. Now if you take these 2 points. Now this pulley P2 is rigidly fixed to the wedge. So with respect to wedge, this pulley P2 is motionless. So this string will do 0 work on this pulley at these 2 points. At effectively 2 points where it is acting. So this becomes T into 0 plus T into 0. 0 plus 0. Okay. Now come to this point P3. Now this string exerts a force on P3 at effectively only 2 points. At its highest point and its lowest point. Now to find the work done by string on this pulley P3, we must know the displacement of these 2 points of pulley P3 with respect to wedge. Now with respect to ground, wedge is moving displacement dx, it is undergoing. And this is at rest. So with respect to wedge, this pulley P3 will appear to move leftward, a distance of dx. So this point of pulley P3 undergoes a displacement dx with respect to wedge. And this point also undergoes a displacement dx with respect to wedge. And T act in same direction. So it becomes how much? Plus T dx cos 0 degree plus T dx cos 0 degree. Cos 0 degree becomes 1. Now you see this pulley. At this pulley P4, string exerts a force effectively at 2 points, this point and this point. But this so work done by string on the pulley P4 at this point will be T into displacement of this pulley with respect to wedge, which is 0. Because this pulley is rigidly fixed to the wedge. So this T will do 0 work on P4 at this point. So we add a 0. Here also it will be 0 for same reason. Because this point of P4 is fixed to the pulley. So with respect to pulley it has 0 displacement. So work done by T on this point is also 0. Plus 0. Now finally we take this block here. On this T acts in this direction. And with respect to wedge it is undergoing a displacement dl in downward direction. So work done will be T dl cos 180 degree. Plus T dl cos 180 degree, which is simply minus 1. This adds up to how much? 0. Alright. So see, writing down the constraint equation in wedge frame is much more easier as compared to writing down in ground frame. So this is the advantage of constraint theory, alright. You must understand this very clearly. So now we get, what do you see? We get 4T dx minus T dl is 0. Now T cancels out. So dl becomes how much? 4 dx. Okay. So dl becomes how much? 4 dx. Now we replace the corresponding displacements by corresponding acceleration. They will have the same format. Why? Because there are no variable angles in the problem. Okay. So we replace dl by what? V. And we replace dx by what? A. B barabar 4a. So again by second method also we obtain the same constraint relation. Now just we have to solve these 2 equations, first, second and third, to get the required answer. Okay, fine. So we have to solve these 3 equations to get the required answer. So I T eliminate from this and substitute it in this one. So in this, what do you see? T is equal to mg by 2 plus ma root 3 by 2 minus NBB is simply 4a, that is T. So T I have written twice, no problem, okay, fine. From this and B 4a, I substitute here B 4a. So T becomes mg by 2 plus ma root 3 by 2 minus 4ma. This becomes T. Alright. Now this T, what I do, I substitute in this combined equation and B I write 4a here. So 4T. 4T is this much. In this equation I substitute 4T. So 4T becomes 4mg by 2. 2mg plus 4ma by 2 minus 16ma 4t equal to 5ma minus b also becomes 4a. So 2ma root 3. 2ma root 3. See, now m will go away. Common term m cancels out everywhere. Fine, alright. So now I've got the final equation. I love this diagram, okay? Now what do we get here? 2g is equal to 2g plus 2a root 3 minus 16a minus 16a is equal to 5a minus 2a root 3. Okay, so this becomes how much? 2g equal to 16 plus 5, 21 minus 4 root 3 into a. Okay, so a becomes how much? 2g by 21 minus 4 root 3. It is therefore the required answer. Okay, so a becomes how much? 2g by 21 minus 4 root 3. This is therefore the required answer. Okay, this problem I have fully demonstrated how to solve the question. Okay, I have demonstrated the essential concepts of the constraint theory. So you can apply the constraint theory in any frame of reference. This I have already stated. In this problem I applied the constraint theory in two different frames. First I applied in ground frame, then I applied in wedge frame. In both the methods we have ultimately obtained the same answer. Okay, so you go through this properly. If you are in any doubt, you would write doubt in the comment box. I'll clarify it. Okay, this I close it here. Fine.